Hello, so today we are going to do this Leetcode BD challenge, part of April Leetcode challenge, kth smallest element in a BST. So the problem says that we get a root of a binary search tree and an integer k, and we want to return the kth smallest value, and this is one indexed. And so, for example, if we take a look at here, we have k is equal to 1. And then we have this tree here. Now k equal to 1, which means the first smallest element, which means just the smallest element, so that's just 1. Okay, and you can notice here this is the leftmost element. And in a binary search tree, the smallest value is the leftmost element, and then the one next to it on the left side is the second smallest value, if there is one, that is. If we take a look at the second example here, k is equal to 3, and so we want the third smallest element. So the first smallest element is 1, and then the second smallest element is 2, and then the third smallest element is 3. Okay, so yeah, this is pretty much the problem. Now, one thing you will notice is that if we do the in-order traversal, which starts from the left side and then does the root node and then the right side, we get a list in a sorted order. And so if we get a list in a sorted order, to get the kth smallest value, we can just get the element in position k, and in this case k minus 1, because what the problem says is that this is 1 indexed here, right? And so we could just do the in-order traversal. We can do it recursively, and then just get the leftmost, get the left element first with the in-order traversal, then the node, then whatever is on the right, and then we go to the parent again, and it's just a simple in-order traversal, and we collect the values in a list and then get the element at the kth position. So yeah, this solution is pretty straightforward, so let's just code it up right away. So what we need to do is, so just in-order traversal, and that does left side, then the node, then the right side. And so if we can just code that up here in order, and we need to pass a node, and then we need to recurse on both, first the left side, because that's what we want first, then we need to process the node, and then we need to do in order on the right side. Okay, now for us, processing the nodes is just adding the node value, right? So if we let's say, for example, want to put this in a list, we'll do it simply first with a values array that we initialize outside of the call, and then call in order on the root. Now here, to process the node is just adding it to the list, values.append. And what this will do is it will keep recursing on the node.left on each call until we reach the last node on the left side. And so we need our base case here for when the node is null, we reach the end of the tree, we want to return an empty list, right? Because nothing is there. Now, when we reach the leftmost element, we will add it, and then our recursion will pop up one level, and then we will, so in this case, our recursion will pop up to 2, and then we'll add 2, and then it will pop up to 3. And so until we get to 3, then it will go to the right side. And so now that we have all the values in self.values, we could just return the element in position, the kth smallest element. And since k is considering that we are 1 indexed, and the list here is 0 indexed, we need to return k minus 1. Let's run this. Let's use all examples, and let's submit. And this passes all test cases. Now, one small thing we can improve here is not use the self.values. This is not very nice to reference inside of another function. And so what we can do here is just have the function return the values. And to do that, we can just, instead of doing this, we can add the value as a list of one element, right? And we want to add this to whatever is returned from the left side. So that way we get exactly left node and then right, and here we add it as well. And now we could just use values, the return list of values. And we can run this. And here, what? Okay, we need to return this. Yeah, sorry. Okay, so if we run this, okay, that should pass. And that passes test cases. You may see some people, instead of doing not node, do like node and this, and then just maybe do something like this, which would basically, yeah, shorter, arguably less harder to understand. But yeah, it amounts to the same thing. Basically, if node exists, we return this. Otherwise, we return an empty list. Yeah, so that's the recursive approach. One thing we can think of is, okay, can we get rid of this extra space values and just get the kth value while we are traversing the loop? And yes, we can do that. We will first use just extra properties on the class. That's fine sometimes, but yeah, let's start with that. So let's try to get rid of these values here. And now we will keep our in order. It's just we will not be returning a list. And we'll keep track of two things. We'll keep track of the count of the elements so far, okay, that we traversed so far, and then we'll keep track of the kth element once we find it. Okay, so initially it's none. We'll assign it here, and then we'll return it once we find it. Okay, now what should we do here to get it? So each time we process a node, we should increase the count, right? Because when we get here, we would have went into the leftmost element, so we'll be at 1. Okay, and when we visit 1, we want to increment k because that's the smallest element. If we were looking for the second smallest element, we will do k equal to count equal to 1, and then we'll go to 2, right? Because then the next call. Okay, so we need to here increment our count in the processing phase by 1, and only if the count is equal to k minus 1 because of the 1 index, then we want to set the kth node or the kth value to be equal to node above. Okay, and that will be what's returned here. And so that's pretty much it. So this is the processing, what we do in the processing phase. One thing that so it looks like it was not set. So here we need to do this after, right? Just in case k is equal to 1, we want the first one. Okay, so that works. Now let's submit. And that passes test cases. Now, one thing we can avoid here is what I said is that earlier, which is that if, let's say we want the first value like here, we'll still unnecessarily process 3 and 4, and so that's not really needed. So what we can do is just stop here if self.count is bigger than k, or actually equal, then we can stop. And that passes test cases as well. Yeah, and this is all then because we process all the nodes in the tree, and we are only using these two variables, so constant space here. Yeah, so that's pretty much it for this recursive solution. It's not very nice that it uses like self, and so if you want to try to avoid these, we can do it easily with an iterative approach. So doing the in-order traversal, but in an iterative way instead of a recursive function here. So let's explore that. So to do the iterative version, we'll need a stack, and we need a pointer to traverse the routes, to traverse the nodes, since we are no longer doing a recursive function. So we would have our node assigned route. And while there is still 8 elements in the stack that we need to pop up in process, or we are still traversing and we have a node. Okay. Here, the first time stack is empty, and so but current has a value, so this would work. And now we want to go and explore all the way to the far left. That's what we need in the order traversal. We know we need to go all the way to the left node. And so to do that, while current, okay, we'll keep going left. So that would be current.left. But as we go left, right, we want to add to the stack the element, because later we want to pop it and check if it has a right element. And so to do that, we will do stack append current. And now if we exit the loop, that means current is null, which means we reached the end. We reached the far leftmost node. And now it was assigned to current.left, which is null. And so in that case, we want to pop the latest element we appended, and that would be the leftmost node. And now this is the processing phase. So this is the traversal to the left side, and this is the processing phase, and we'll do similar thing to what we did in the recursive version, which is, so let's have here count, similar to the recursive version. We'll increment it, and we'll check if count is equal to our value, which is k. Then we want to return the value in that node that we are processing. Otherwise, we want to go right and then continue. So an example here would be, okay, let's say we have a tree like this, 2, 1, something like this, and then at 2 maybe we have, or at 3 maybe we have 4, and then at 4 we have maybe 5, and maybe we have, let's say, I don't know, maybe 6, and then maybe 5, like this, right? So when we reach 3, we want to go to 4, and then with the loop we'll go again, right? And we'll still have an element, so for 4 we'll go to the right side, which is 5, another again, right? And if 4 had some left children, we'll go here first and process those. And so each time we'll process the left side, the node, and then the right side. And then at the end we want to return. At the end we're already returning actually, so we don't need to return anything anymore. So that's pretty much it. So let's run this. And that seems to pass. And that passes test cases. Slight improvement, just small thing we can do here is get rid of this count. Not really a big improvement, but still a little bit nicer. We can decrement k each time, and when k reaches 0, that means we have the kth smallest element we can return. And that passes test cases as well. Yeah, so that's, I think, pretty much it for this problem. We saw a couple of solutions. And here we will return before, as soon as we find the kth smallest value, we'll return and not do any additional processing. Yeah, so that's pretty much it. Thanks for watching, and see you on the next one. Bye.